Right, this is Muirhead's inequality part 2. Part 2. We need a new notation here. We need a new in fact we need several new notations. It's quite hard, this. There's quite a lot going on here. I'm going to consider, I'm going to define this. This is the sum over all permutations. That's how you say it. And I'm going to give you an example. Sigma factorial of f of x1, x2, x3 equals, let's see if I can get this right, f of x1, x2, x3, that's 3, plus f of x1, x3, x2, plus f of x2, x1, x3, plus f of x2, x3, x1, plus f of x3, x1, x2, plus f of x3, x2, x1. So it's all six permutations of the three arguments. All 6 permutations. Okay, so that's what that means. And of course, if I had more, some function of x1, x2 up to blah 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 up to, let's say, x15, then I would have 15 factorial terms to add up. Okay, now I'm going to consider I'm going to do it in this one. I'm going to consider f of x1 up to xn to equal x1 to the power a1, x2 to the a2, blah 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 up to xn to the power an. Oops, keeps on doing that and I don't know why. So that's my function, and I'm going to make a new definition. I'm going to say if alpha is a sequence, let's say alpha 1, alpha 2 up to alpha n, if alpha is any sequence, then I write in square brackets alpha, that is going to equal 1 over n factorial times sigma that of x1 to the alpha 1, x2 to the alpha 2, all the way through to xn to the alpha n. Okay, so now we need some examples. So I'm going to write alpha for the sequence equals, let's say I'll write it like 3, 2, 1. So what is that? Well, by definition, it's 1 over n factorial, which is 3 factorial here, times this function here, but overall permutation. So I'll write the first one. It's going to be x1 cubed times x2 squared times x1 to the power 1, I guess, plus, now what I'm going to do is I'm going to permute the x's but not the alphas. So it's going to be x1, x3, x2. There's going to be other terms here as well. It's going to be to the power 3 times 2 times 1. And then of course here I've got x2, x1, x3 plus x2, x3, x1. And that's going to be to the power, it's always the same power, 3, 2, 1, 3, 2, 1. I'm just slotting in the powers there. So let's do the other ones. x3, x1, x2, and there's x3, x2, x1 to the power 3, 2, 1, 3, 2, 1. There we go. And it's a sixth of all those, so it's kind of an average. It's kind of a, it's actually written the symmetric mean. This is the symmetric mean of alpha with respect to x. I mean, it's got x's in and alphas in, but there it is. That's great. But something peculiar happens. If I say alpha equals, let's say, 2, 2, 1, let's try that. What is symmetric mean of alpha? Well, it's 1 over 3 factorial, which is 6, of course, times, it keeps on scrolling and I don't want it to, times, let's put everything in brackets, it's going to be x1, x2, x3, x1, x3, x2, x2, x1, x3, I'll put the powers in later, x2, x3, x1, x3, x1, x2, x3, x2, x1. To the power 2, 2, 1, 2, 2, 1, 2, 2, 1, 2, 2, 1, 2, 2, 1, 2, 2, 1. Okay? Equals 1/6 times. Now what we're going to see here is that when we swap x1 and x2 over, they're the same. Because look at this term here, this term here, this first term here, and this term here are the same. Because all I've done is swap x1 and x2 over, and they are both raised, x1 and x2 both are raised to the second power. So x1 squared, x2 squared is the same as x2 squared, x1 squared. It's just commutativity of multiplication. So here I've got 2 x1 squared, x2 squared, x3, that's that term and that term, plus 2 x1 squared, x3 squared, x2, plus 2, 1, 2 times 3, 1, 3 times 2, we've got x2 squared, x3 squared, x1. Okay? That should be a curly bracket there. And that's a 1. Okay? Yeah, there's different forms of the theorem, but I prefer this one because it reminds me, this 1 over n factorial here reminds me I should have n factorial terms in the bracket here, some of which might cancel out. So altogether it's equal to 1/3 of x1 squared, x2 squared, x3 plus x1 squared, x3 squared, x2 plus x2 squared, x3 squared, x1, which is a perfectly respectable sum, quite a nice little thing there. Of course we can factorise it a little bit more if we want. I could write it x1, x2, x3 over 3 times x1, x2 plus x1, x3 plus x2, x3. You see, it's got this kind of nice, pleasing symmetry associated with it, which can be very useful. Right, I'm going to stop there. This is what a symmetric sum is. That is the definition of a symmetric sum. Stop there.